So now we would like to give the proof for Newton's theorem. So let's get the proof. And to give the proof, I'm going to consider two different variations of the field. So here's the first one. I'm going to imagine that phi goes into phi prime plus delta phi. And what I will tell you is I'm going to assume that phi obeys the classical equations of motion. Now, we derived these when we studied the Lagrangian formulation for the field. And let me just remind you, we learned that the derivative of the Lagrangian density with respect to phi is equal to d mu of the derivative of the Lagrangian density derivative with respect to d mu phi. Good. So that was the classical equation of motion. But we're going to say that delta phi can be anything. So you pick whatever delta phi you want, but we will assume it's small. And by saying it's small, we really want to be able to assume that we can work to first order. So we'll use a first order analysis, okay? So that's the content of us saying that delta phi is small. So let's work out what the change in the action is under this first case. So delta S will be equal to an integral d4x of the change in the Lagrangian density. And that's rather easy to calculate. That's an integral d4x. Then we should differentiate the Lagrangian density with respect to phi, multiply by delta phi, plus differentiate the Lagrangian density with respect to d mu phi, and then the change in d mu phi. And I want to remind you of one other fact. When we derived the Euler-Lagrange equations, if you remember, we said that delta d mu phi was actually equal to d mu delta phi. So I'm not going to go through that again. You should probably remember that from when we derived the Euler-Lagrange equations for the field. If not, go review that video again. I think it's lecture number 9. Okay. So now I can rewrite this change in the action. This is the change in the action. I can rewrite it as the integral d4x of. Now, instead of writing the L d phi, I'm going to use the Euler-Lagrange equations to write this as d mu of dl d mu phi times by delta phi. And then for the second term, I've got the L d mu phi. And then I've got d mu delta phi. Now, if you stare at this for a moment, I'm sure that what you will notice is that what we have written down here is a total derivative. So we've got an integral d4x of d mu acting on dl d mu phi delta phi. When we differentiate the first term using the product rule, we get the first term in the square brackets on the line above. When we differentiate the second term, we get the second term in the square brackets on the line above. So this is our first equation, okay? Let's call it equation number 1. And we derived this equation by assuming that phi satisfied the classical equations of motion, and we assumed nothing about delta phi. Good. Okay. Now I want to consider a second variation. I am going to change phi into phi primed, which is equal to phi plus delta phi. And I'm now going to assume that phi is anything. And what I mean by this is it need not solve the classical equation of motion. Okay, so I'm not assuming that phi solves the classical equation of motion. But when I look at delta phi, well, I'm still going to assume that it is small, because I still want to work to first order, but I'm going to say it's a small change due to symmetry transformation. Okay, so I'm just going to write trans for transformation. Good. And let me just give you an example to illustrate what I mean by this delta phi. So here's an example. Let's imagine that we were looking at translational invariance. Okay, so that's our symmetry. Then what would happen? Phi of x would go into some new field, phi prime of x, and this is just phi of x minus a. So a would be the parameter of the translation, and this would just be phi of x minus a mu d mu phi. So two things to note. First of all, we would take a mu here to be infinitesimal. And we do that to justify the fact that we want delta phi to be small. And then what we mean by delta phi is that whole expression there. That's what delta phi would be if we were considering translations. Okay? Now, in this situation, what did we say was the definition of a symmetry? Well, a symmetry transformation leaves leaves the value of the action unchanged. So that means whatever delta S is, it must be zero. That doesn't mean it's identically zero, but it does mean that it should be a total derivative. Then this would be a surface term. And as we've discussed, because the fields fall off to zero at infinity, the surface term will vanish. So this would be consistent with delta S is equal to zero. Let's call this equation number 2. Now, next we need to make a clever observation. You see, we derived the expression 1, assuming phi obeyed the classical equation of motion, and delta phi could be anything. So in particular, delta phi might have been the change under a symmetry transformation. Secondly, we derived the change 2, assuming phi was anything, but delta phi was a small change due to the symmetry transformation. So 2 should still hold even if phi does obey the equation of motion. So if phi obeys the equation of motion and delta phi is a small change under a symmetry transformation, then 1 has to equal 2. And when we say 1 has to equal 2, delta phi could be any change due to a symmetry transformation. So there's an infinite number of delta phi's that we could pick here because there's an infinite number of symmetry transformations that we could do. And when we say phi has to be a solution to the classical equations of motion, well, it could be any solution to the classical equations of motion, and there's an infinite number of those. Well, because 1 and 2 match for an infinite number of delta phi's and an infinite number of phi's, it means actually that the integrand of 1 has to match against the integrand of 2. So we learned that d mu, dl, d mu phi. Well, what happened there? Times by delta phi So this is from 1. This has to be equal to d mu f mu. And again, the integrands match because the matching of 1 and 2 holds for any solution and any symmetry transformation. But that means that d mu of dl d mu phi delta phi minus f mu is equal to 0. But this we can write as d mu j mu, where j mu is equal to dl d mu phi times delta phi minus f mu. Great. So now we have indeed proved that there's a conserved current, and we've even obtained a formula for that current. This current is often called the Noether current. To derive it, we had to assume that we had a symmetry, and in fact, delta phi has to be a small change under the symmetry, and f mu was the change in the action under the symmetry. So both delta phi and f mu are defined by the symmetry. And the second thing is, you have to evaluate J mu on a solution to the equations of motion for J mu to be conserved. Because to equate 1 and 2, we had to assume that phi obeys the equation of motion, and we had to assume that delta phi was a small change under the symmetry transformation. Great. That completes the proof of Noether's theorem. We'll continue in a moment.